give like, my plan is to write down like to a version of Word, like the simplest version of it, which contains some of the complexity. Then we can kind of like talk about what things right now there are easy gains to go on, what things are harder gains, and then we can see how to go. And can you guys all see this board? Okay.
You make it larger?
Okay. So your perspective is Da Vinci. Okay. So I'm gonna talk like there are so the current optimized version of Word with some of the things that are not in the paper, but then we found out later. And then, yeah, we can tell you a bit about what's going on. So, I'm gonna think it for a PCS for the moment. There's some optimization there where we don't think it about as a PCS, but then we can go on later. Okay, so suppose I'm giving some multivariate polynomial, multilinear polynomial, I'm gonna say m variables.
Do you want 2 of them?
Sure. I'll start with this one and then we'll move on. It will just keep rotating for those things. Okay. Exactly.
Can you mirror?
Like I can, yes. So, okay. So where we'll have like 2 parts. So a commit phase and an evaluation phase. Okay, what's the commit phase? Okay, the commit phase. So first of all, we're going to be choosing some with Solomon code. Say over the same field, over some domain, and I will want it to. So okay, the first thing I want it to do is some value k, which is n. This will be the folding factor. The folding factor is important because this is like how much can the word fold in the first round. So at each step, when we're gonna put so k, so if k is 1, I'm gonna be folding by 2. If k is 2, it's gonna be folding by 4. If k is 5, I'm gonna be folding by 32. This read Solomon code needs to be able to encode 2 to the m minus k values. So this is 2 to the m values. I'm gonna like think of it as like this is a matrix in which I have like 2 to the m minus k and k. Right. This is what I should have in mind. So it's 2 to the k. All right. My commit procedure will be that I will commit to an interleaved Solomon code word. So effectively what this means is that like I'm gonna let it called f and will be equal. This notation is means the interleaved things, and I'll explain what this means. This means that I basically look at each row and I encode each row individually. This is fine. Then I will send like row f. So I will do a Merkle commitment of f. This is my commitment. This is not actually done because we're working in list decoding, so you need something more. You need an out-of-domain sample. What's an out-of-domain sample? Well, the verifier will send me some randomness, and I'm going to keep it a bit unspecified because we actually have a lot of freedom in how we choose this, and it's not exactly clear what's the best way for efficiency and soundness, but verifier will choose some challenge, and then the prover will send the value of p on this challenge. So in this case, okay, let's say for this one, I'm going to just say I sample as a multilinear challenge, S, and I'm going to just, the prover will just send this. So my commitment is the Merkle root plus this value. And of course, it will be done by Keshamir in reality, of course.
Up until this point, can we live in a smaller field and then the verifier sends a larger field?
Yes, absolutely, absolutely. Like we can say that this is over B, and this is over B, and this is over F. Yeah.
I think this is one of the first optimization we have made because this is more convenient to have everything directly transferred to the extension field, but this is not performant at all.
Yeah.
So up to this point we keep in the base field.
Exactly. So these are like kind of like base large field multiplication.
Yeah.
Alternatively, you can also play around with this. So in reality, I can also choose S1 up to SL. And roughly, if I do this, like I get like, I can choose smaller like sample sets. So for example, I could choose this to be base field elements, but then I have to do more of this. So there is one trade-off, I think, in some of the old version of Plonky. This is something you can also do in Fry. It's not really relearning, but usually what we end up doing, we sample 2, I think, in the current implementation, 2 auto domain samples. So think that 2 auto domain samples, and so this invokes 2 multilinear evaluations. Okay, so this is basically the whole commit phase of work. So here there is not that much you can do to optimize, right? There's the FFT. You know, you make a better FFT, you get a better protocol. There's a Merkle tree commit. So if you have a Merkle tree, better Merkle tree, you do this.
We also gain there by doing packing inside the Merkle tree. Initially, we had no packing, but then when you hash the leaf and everything of the Merkle tree, you can do packing of the hash function you choose, in our case Poseidon, and you gain a lot.
Yeah.
Also something is that in our case, we need to have like Poseidon for the recursion reason. And so if you choose Ketchak or Blake tree there, it will be much faster, but we cannot do that.
And you also, of course, like when each of the leaf of the Merkle tree will have side to the decay. So this is like a Merkle tree. Yeah.
Sorry, I was just gonna ask for, you can finish what you were saying.
No, I'm just saying like the Merkle tree I want to commit with like leaves of side to the decay. So depending on my choice of case, this might be a bit of hashing. These are base field elements, but this is yeah, you have to take care of this.
Okay, so rho is what, the flattened multilinear coefficients?
This one?
No, the rho hat or whatever?
Rho after, yeah, so I'm gonna be thinking about this, that this is represented in rho is the evaluation of rho over the binary hypercube.
Yeah, so Lagrange, but you implicitly flatten it, or maybe not, but regardless, then Reed-Solomon, this is C2 to the K?
Yeah, this is the interleaved version.
Oh,
of this.
interleaved, okay.
Yeah.
And then, okay.
Yeah.
Okay, and then you said the verifier samples 2 points.
Yes. Yes, I call
I don't know
them.
why there are dots, right?
Because you could do more.
Okay.
So basically, the error of this step roughly is the list size of the decay. Anyway, it's the same. It doesn't really matter. Times m to s. So this is the error that you get in this step. So roughly you can very efficiently amplify. Like if I instead of this is what did I use there?
Oh, okay.
Yeah.
Okay,
So,
and then rho hat of S means what? Like a univariate evaluation?
no,
or-
in this case I'm doing a multilinear.
Okay, okay.
But you
Oh,
can also
okay.
do a univariate. You can do a multilinear. You can do your favorite thing. Like in fact.
And does the verifier even read that, or is that only used by the emulator? Like, what does verifier do with rho hat of S?
So at the moment it doesn't do anything.
Okay.
In the commit phase it just reads it and stores it.
Okay.
Then later on when we do the evaluation we will prove this as well.
And there should be SI for each SI you sampled, right?
Exactly, yeah.
Yeah.
Yi is equal to Si. So you do all of them, and this is the whole commit phase. So like my output of this is the commitment to F, and then Y1 up to YR. And point of freedom here is that this thing actually works for anything which is a epsilon bias generator. So you can choose like univariate evaluation, you can use multilinear evaluation. You have a lot of freedom on this. You can use select, actually, funny enough. You can also use select here. There's a bunch of different choices that one can make here. Each of them will give you like slightly different errors and slightly different things over here, but I think the multilinear setting gives you a pretty good error without much drawbacks. So to me, this is a relatively good one to start with. And it'll go kind of well in this point because, so this is the commit phase. Yeah, there's another optimization here which I can tell you in a moment. So in our protocol, right, we will have prover and verifier. Like at some point, the prover will send a commitment to its witness, which I'm gonna assume is some multilinear polynomial. Something will happen, usually a sum check. So there will be some sum check here. And then at some point, I will have to prove the W at some random challenge that comes out of this sum check, say gamma, is equal to some value, say 0, for simplicity. So I run this commit phase, and now I want to prove this. So,
Sorry.
yeah.
A small question. The bigger L is, the larger the commitment
Yeah.
is. Can we actually fold them into like one field element by taking a random element and just, you know, taking
The biggest L is.
Yeah.
You can, but I think this L will be 2 or 3, so it probably is not worth it. Like, I don't think of a setting in which L should be bigger than 2.
Well, I mean, there is a world where you make L large and you sample the base field.
Yeah, absolutely.
Like, I think that might be very interesting because then your commit will be entirely base field.
Exactly.
Which potentially would work a lot better for the univariate stuff.
I think so, especially because the sum check we'll see the sum check ends up.
Just on the base field.
Exactly.
That might be something we should do.
Yeah, so
Yeah.
the eval egg then.
Yeah, we can get to it.
Yeah, yeah.
Why they are out of domain? Why does it need to be out of domain? You said 2 of the things should be out of the domain.
Yeah, so these things are the outer domain sample.
Why? Why should be out of the domain?
So because effectively when I'm doing this reduction, so I want the prover to commit to my witness, and to me it's important, like when I commit, there's only one thing that the prover has committed to. So in particular, you know, suppose here like the prover could send you like something which is like not a real code word, but something which is corrupted, and then there might be many different close things to it.
You're helping the emulator. You're giving the emulator more content to work off of.
Yeah, but
If you didn't,
my question is like, since this stuff is like non-interactive, what happens if it turns to be into the domain? Because like in normal like try,
Yeah.
you use like I think what is like deep.
Yeah.
Like, do you have a trait that you?
So this is effectively is like deep.
Okay.
It's like deep to you know an out of domain sample to eliminate pretenders.
Okay.
I just want to make sure there's a
Thank you.
single one, and I'm happy with that.
Right.
if you didn't, then just for intuition, the emulator has nothing to go off of except for this row. And by list decoding, there can be many code words that are near, sorry, not row, but what did you call it? F.
F, yeah.
F. There can be many code words near F. If you didn't submit more information, then there's no way for the emulator to narrow down out of the whole list which one is the right one.
Exactly. So now we have like, this is the initial part.
Sorry, one small question. What does out of domain here mean? Out of the hypercube domain?
Out of the L. So for me, like, I will queries, they're slightly different, but yeah, this makes more sense in the univariate setting, but it will make sense. So if you think about the Rich-Solomon code, right? The Rich-Solomon code, their evaluation of some univariate polynomial, and I know them on L. So this is my in-domain things.
Ah, I see.
If I were testing them in the rest of the field, they would be out of domain. In this case, this doesn't really match because this is a multilinear point and not a univariate point. But it's because morally they come from the same place, so we still count them as out of domain. Like
So each component of that multilinear point is coming from the out of domain for the Reed-Solomon evaluation domain.
Here things are a bit muddy for the reason that basically originally when we were doing these things, these were actually, we would tell the prover to interpret Q as a univariate thing, and then each one of them will be a single field element.
Okay.
And turns out you don't need to do that, and you get better soundness, but the name stuck without the domain. So this is like, I'm thinking of I'm keeping everything multilinear. The univariate part is going to be important, and it comes in because of the Rich-Solomon, but not for this part.
Okay.
But I'll explain where this comes in.
Just a quick question from my side, because I'm trying to sync with my own variant of WHIR that I have in the base code paper. So the difference is you directly commit interleaved so that you spare the cost of a large FFT.
Exactly.
And where's the folding randomness? I didn't get that one.
No,
We're not there yet.
They haven't voted yet.
So you, because I have it in a different order. So in my version, I first get the folding randomness, and then it's about the out of domain.
No, for me, first I commit, I do the out-of-domain sample, and only after that I start folding.
We haven't started WHIR yet.
Yeah,
We're
at the
still
moment
just,
it is-
So this was already forecast.
right
Yeah,
now we're
was it?
encoding a polynomial P.
Yeah,
and
this is
we're
just the
taking it
commit
out of
phase.
domain,
Yeah.
and
Yeah.
later we're going to use WHIR to prove that P is close to.
So
its
nothing, no verifier randomness yet.
So far, just
Just
for the
yes,
out of domain.
just
sample.
out-of-domain sample.
Yeah, but that's already different than to the version I
So
have.
we're just setting up the statement. The statement
Yeah.
is I have something that's close, and the evaluation at these points is
Yeah.
Y.
Yeah, so
I did it differently. So
So
I saw you.
for this, like, yeah, we can chat about it later, but
Yeah.
the way I think about it is when you commit, then you do the out-of-domain sample because that fixes a single witness. And then only later on, at the very end, when you know which point you want to prove, then you start the things, which also will go to domain samples, I would say.
So I had it just switched. You know?
Yeah.
You only commit comes folding check.
So you commit with only the start without the domain, then you fold and you auto domain.
Then you fold, they get the folding randomness,
Yeah.
and then you get also the question for the out of the value
Yeah.
of the out of the fold.
Yeah.
Of the fold. So it's
Yeah, I think it probably also work. Yeah, I think it should.
that's
Yeah, because you have the
what's
proof.
the security proof is
Yeah.
for. I hope that this is not a big.
Yeah, no. No, I think yeah, should fine.
But the advantage is that the out-of-domain sampling is on the folded polynomial, so it's like easier to compute in your case.
What is?
Yeah, because it will be like smaller
Different
thing.
error bound for that. 'Cause,
Maybe you get a different.
the adversary now has many polynomials close to F. You fold them, he has like a higher probability of something bad happening with the folding. And if that happens,
Not really. I was thinking of that way. So whatever you have committed, just as set of values. Don't talk about approximates and polynomials. It's the predictor for not in domain evaluation for the next oracle. It's really the predictor.
Like I think what would happen if you do
And,
that, you
and
get.
I actually needed to, if you say you have approximate for a new oracle,
Yeah.
I needed to choose one of them to have consistency with, let's say, not just few samples, but really a large subset of.
Yeah. No, I think you can do it. That what you get, the difference is that with this approach, you get the error of the polynomial IOP does not depend on this side. The way that you would do it in that case, you would work with like a list IOP, so you pay like some more errors there. You still can handle them, and then later on you can do a cheaper out-of-domain sample. Both things work. But let's continue. I'll finish the. Yeah. So okay. So now we have like. We want to open with WHIR, and it's important to figure out what are the claims that we care about. So, as a PCS, so we have like, I'm gonna actually rename the witness to P just for consistency with other things. So, we're doing multilinear, we only have one tool, which is SumCheck. So, what we'll do, it will turn all of these claims, so we have 3 claims, well, 2 claims. We have the out-of-domain sample in the commitment, and we have the things that we want to show.
Wait,
Yeah.
sorry to rush in here.
Yeah.
So, what's the S? So it's a multilinear.
Yeah.
So is this the evaluation query?
No,
for
this is the
pure?
out-of-domain sample. So
This is already part of WHIR, so not of the claim to be opened.
this is part of the commitment. When I
This is the claim
commit,
to be opened.
Yeah.
I claim that P of S equals Y.
Ah, okay. So
Yeah.
so I'm missing.
So
It's
you're on the same
interactive
page.
commitment phase in
Correct.
which the verifier samples random evaluation points. But these are not the evaluation points. We haven't even begun the evaluation
yeah,
protocol.
this I'm just
Right?
committing.
Okay, so no evaluation proof yet. It's
Not
just
yet. This is
it's
all
just the
commitment.
preamble.
Yeah.
I have committed to something.
Yeah.
It might be even non-random. The S. No.
No, you need it because I need to short zipple the list. No, because I need to identify one single element of the list.
For what?
Well, because I need to do the autonomy sample. This is like, I need to identify one single element in the list.
But I mean, the commitment could be thought in a wider sense, no? Right, so you don't, like, that's what's in the Redshift paper, it's a list
yes,
commitment.
yes, so so here I'm for a polynomial IOP, in which the prover sends a single unique polynomial. This is what the analysis is. You can think of like list commitments, and this is what Redshift does. It's true. You get some worse error, but I'm doing this at the moment just for
so you want to have really a standard PCS.
I want to have exactly. I want to compile a standard.
So then we're talking about completely. I was addressing completely different things.
Exactly. Yeah. This is for like the unique case. Yeah, I agree. We can do it for the list, but we need. Yeah. Okay. So we have some claims, and the claim that I have is that for all I in L, pi at si is equal to yi, and then the claim that comes from this commitment thing, which is that p at gamma, which I'm actually gonna call it f0 because I'm lazy, is equal to y0. So I'm gonna move here. These claims by standard standard tricks in multilinear, this is they're equal to like the claim that for all I, now I'm going to put in up to 0, up to L, the following sum check thing holds. S I B times P at B is equal to IR. This is the usual trick that you do in like in the multilinear sum check. I'm just rewriting these things in this way.
Right now, so S naught is going to be an extension field, right?
S naught is going to be an extension
S
field.
naught is the actual evaluation.
Yeah, exactly.
Okay, so
there is another trick we can do to turn that bottom one into like a selection of base field things, which I think we do in multi-field, which is what.
Because you do like you run many sum checks.
Well, it's just like an extension field point is the same as like n base field points,
Yeah.
because P is base field. So you,
Yeah,
can split it up into n.
Yeah.
So if we do that, then the eval egg that is on the
Yeah, you
subject
can
will
make
be
everything
base
base field for now.
field,
Yeah.
and then it will be much more friendly to the univariate
Yeah,
scheme.
that's the
Yeah.
idea. Yeah.
Because right now, like the steps between like on the right and on the top, between the constraints that you wrote there and the egg polynomials that you wrote there, this is 25%
Of the random,
of the total WHIR.
So like getting down to the base field might be.
Yeah, it's something that we definitely should try. The other thing you can do, which is what Ulrich was also saying, is that basically if you avoid the delta domain samples and you pay a bit more errors over here, which you often can afford, you can often avoid these to have like these initial auto domain samples in this part of the protocol, because they can work like with the yeah, you pay a bit more errors here, but it's kind of usually fun.
Just S0?
Yeah.
Is it also the verifier?
Yeah,
Yes,
S0 is,
it's
yeah.
kind of-
Usually what happens is that you run a sum check, and the sum check randomness will become your S0. And I just, yeah.
Ah, okay.
Yeah, this is like what happened in the protocol. I just re-indexed because I'm lazy. Okay, so now we can start thinking about the open phase of WHIR, where I kind of like open these kind of things. So the protocol in itself is, I want to say not too bad. So, okay, what's the first thing? Well, I have many claims. I don't want many claims. I'm gonna take a random combination of them. So this becomes the claim that whatever, sum over epsilon to the I of sum b blah is equal to sum epsilon to the I of time yi. So this is the first step, and this is I can do it. No, there's not a problem. Then I'm gonna start reducing the problem size. So what I'm gonna do a sum check. So, but not a full sum check. I'm gonna stop it. When I'm gonna stop it? After k rounds. So my like k will determine how many rounds of sum check I do. So I can do simply h1, then I get gamma 1 up to hk, and then I go up to gamma k.
Here there are some tricks that you can play with k, no? Play
Exactly.
with the variable k, so you can stop sooner or later, like the sum check, so that you can give
Exactly.
more work at the beginning and less at the end.
Exactly. So yeah, here you can play a lot of tricks around here. You can also defer. Typically, there's gonna be another FFT, well, another few FFTs. So also having these large, so these FFTs are like cheaper, is not bad. Like the trade-off is that later on, when we query by the verifier will need to read the column. So we don't want to make this too large because otherwise each query the verifier will read a lot. So there is like a prover verifier time trade-off. Like if you make this square root of n, for example, then you get the arrow, funny enough, which is nice. Okay, so cool. So what do we do now? Now we folded a bit, and if you think about it, if you look at these claims, what does SumCheck do? SumCheck will fix some of the values of beta to the gamma xi. Turns out that if you look at the evaluation is multilinear polynomial, these will also get like folded in exactly the same way. So what I will do now, I will send, and I'll tell you exactly. You can even just. I will run here commit of piat at alpha. Sorry, not alpha. This is gamma, where gamma is the gamma 1 up to gamma k. So what I'm basically doing here, I'm taking my sum check, sorry, my evaluation, and folding them by gamma to step. This is exactly what the sum check does. And then I arrive to this and I commit.
What the same as fried?
Well, base fold.
Yes. Well, yeah.
Yes.
Isn't
Yeah.
that the same as base? Like
Yeah.
they could, yes.
You can
This is also what you would do.
At this point, yes, but there will be some differences here.
You
So
can see, in a nutshell, you can see WHIR as a base fold with increased redundancy in commit.
yeah, so I'm gonna actually choose like some other code, which is gonna be RS star, which will be like over now the actual extension field. I'm gonna choose another domain L star, doesn't really matter, and I will want it to encode messages of size 2 to the m minus k prime, and k prime is the new folding factor. So k prime will be how much I want to fold next. And here I can really choose whatever I want. Like I can choose, I mean, with the same constraint as before, but my evaluation domain can be whatever I want. So now, again, I will do exactly what I have before, but now with respect to, so I'm gonna say that G, actually Q, is PA evaluated at gamma. So the size of this is exactly 2 to the m minus k coefficients. And I'm gonna again shape them as a matrix, where here I have 2 to the k prime row and 2 to the m minus k prime rows, no, columns, sorry.
Columns.
Yeah.
I think that this is where difficulties start with the univariate skip, because in the univariate skip you don't have like gamma 1, gamma 2, gamma 3, gamma, you replace the for k gamma by 1 gamma.
Yeah.
And then everything is modified starting
Yeah,
from
but I thought that what you can do here is like, suppose that here P is, I fix the first variable to be of degree both to the k or k, I don't know which one of the two.
Yeah.
And then everything just follows out. Because I'm kind of like evaluating that part. I think there's some coefficient evaluation there, but we go back to the univariate skip later on.
Yeah, sure.
Yeah. Okay, so this is what I do, and then I'm doing this commit. Working? Yeah. I'm doing this commit phase again. So I send you this matrix, of course, as a Merkle root. I do my auto domain sample, so S1 up to SL.
So encoded row-wise, right? You didn't say this.
Yes, encoded row-wise again. So yeah, this way. Okay, so we've done that. And now, we're in a bit of a pickle because I need to, here the prover could have sent me whatever he wanted, so I need to check consistency of the two things. And now I told you that this L star can be whatever it wants. I tell you all these kind of things like, Giacomo, how do I check consistency? Well, it turns out that there are some tricks. So I'm gonna first sample some locations, some spot checks. These are the same as in Fry. So I'm gonna, of course, I get the answer to the other domain samples. Then I sample Z1 up to ZT, and these will be elements of this domain L. So I'm gonna just look at one of them. This will be in the domain L. Okay.
So wait, the out-of-domain sample is done on the domain of the previous round?
No, so the out-of-domain sample is over the entire field.
Okay.
Yeah, and it's done on this thing here. So the domain sample is related to the thing that you just sent, always. And now I have this X in L. I can, if I sample one of these columns, the X column, I can compute something which is called the fold. It's the same thing as the Fry folding. So I just compute the fold of F at randomness gamma with X. What does this mean? This is exactly mean I query as a verifier, I query the column, and then I take a multilinear evaluation of the column. You can also do other things there, but let's do that. And now I want to check the consistency of this thing with the fold. Well, how do I do it? Well, if this is really the thing that I want, that means that its encoding as a Reed-Solomon thing will agree with the fold at that point. So in particular, I can think of it like, okay, so let GRS be the generating matrix of this code here. So I can exactly write, so what I want to check is that the Reed-Solomon encoding of Q at the point X is equal to this fold, which I'm going to call Z. So this is what I want to check. So the nice thing is that this is again something that I can rewrite as a sum check claim. So I can rewrite it as sum of GRS at X B times Q at B is equal to Z. And here I'm thinking of this as a matrix with, oh God.
I thought RS of Q hat got committed to explicitly, so.
Yes, this is what we commit. Q at is this thing here. So if this is equal to the message behind, if it is equal to this will have the same encoding. So what I'm saying is like this condition can be checked as a sum check claim.
Well, what I thought you were going to say, which is what Fry does, is relate this guy to a bunch of values of the last oracle.
Yes.
Is that what you're doing here?
Fold F of gamma is the value of the last oracle.
Yeah. Yes.
And I'm relating the new oracle with the values of the last oracle. And I'm writing this as a sum check constraint.
So I'm expecting a sum over a coset. In other words.
But we don't have codecs here because I'm doing things interleaved. So
Okay, then shouldn't that just be the tensor combination of the column sitting over?
Yes.
Over
So
X?
this fold F gamma.
Sorry.
What I'm saying is what you do is that fold of F gamma is exactly like I look at this is the committed the Merkle tree in the first round. I read the column, and then I compute the MLE about it.
Yeah, exactly. So you TensorFold it, that column using gamma, right?
Yeah.
So then why is RS? That's what I don't get. Is why RS?
Because this P in the honest case is Q gamma B. In the honest case. Because in the honest case, this is like, I've also folded, sorry, not Q, this is, yeah, this is a Q, and this is a P. My Q's and P's sometimes they become the same letter. I apologize. I have, I also do very bad lambdas.
I'm not sure if I understand Ben's question, but the main difference is the big domain. It's square, the projected domain is not where we commit the new function. So it's for technical reason. You could do it that way, but we have a blown up second domain anyway.
No, I think I'm good. It's just combining two steps. First is the TensorFold of the column, but then there's also an RS encoding. That column itself should be the RS encoding of something else.
Like, well, the column is not an RS.
It's outside the RS domain. So the previous oracle.
So what I'm saying is that, so I have this matrix. This is the matrix of F, right? This is the matrix F, which is the C to the K of P.
Yeah.
Then I will fold multilinear up to I get like some F tilde, let's say, which is will be equal to the encoding of RS of P fixed at gamma. This is what I have. So okay, now I claim you that I have actually send you Q, which is equal to P out of gamma. Right. So my claim. Sorry, P out gamma is equal to Q. How do I? With this Q is the new thing that I sent you. So what I do, okay, I check that for all I in T, the number of repetitions I choose here, that the encoding of P at gamma this is equal to the encoding of Q at. Well, this part here is exactly the fold of the original oracle at gamma. So this position at the left side and left side. So this is just CQ at F side. And then here I'm just rewriting this condition here, which is exactly this, as a sum check query. And this is what I have. So now, what do I get? Well, I had these original sum check queries. So these original sum check queries, through the sum check, they get turned into a single sum check query of the form sum of epsilon I times sum of P equality Si gamma B times I'm gonna just shift it to Q. So this is the first sum check claims, and then we'll have like more sum check claims, one for each one of them. Which is like for all I in T, we end up having that sum over B of GRS at B times QB is equal to ZI.
Yeah, so we haven't read from the second oracle at all yet.
Not at all,
Yeah,
no.
so
We will read that in the next round.
yes.
Exactly.
So
At the moment I'm just,
the difference
yeah, sorry.
the difference from Fry is instead of reading something from the second oracle and comparing to fold of the first oracle to this,
Yeah.
you instead get the virtual value that the second oracle should take and express that as a sum claim.
Which
Exactly.
is given out of domain for the second.
Correct.
Yeah.
What do you
Yeah,
do
you also
what
have-
you want to read is Q at X.
Yeah.
X is in domain. X is in some domain or something, right? But instead of reading it or any oracle, you write down this sum claim that tells you what the value of q at that point should be. Is that a fair statement?
Exactly. You never read the oracle. You just say, look. I believe this oracle should have this, should satisfy this constraint. Let's write it down, and then we'll check it at a time.
Explain me how the oracle gets to the constraint again.
The value of the constraint x is derived from the first oracle.
So that there
Yep.
is the reference.
Exactly. So this is how I set the consistency with the first oracle. Good. And we have another board, so we're gonna be continuing with the thing. And of course, here I'm also forgetting that you also have like a dagger thing, which is the auto-domain sample that you have there. So just to originally I start with L plus 1 constraints. Now I have L plus 1 plus T plus 1 constraints. And then I just keep continuing it. Okay, so what do I do? Yes.
I just want to make sure that we leave a little bit of time for Nico to speak as well.
Because Nico, sorry, I didn't.
Yeah, because
No, it's not planned. But yes.
Unplanned, serendipitous.
Okay.
So apparently he's been working on Liharito, and that has a lot of parallels with this.
Yeah.
Yeah.
There's a bunch of performance optimizations.
Yeah, or at least just discuss like the comparisons, like because it is interesting and might help the implementation.
Absolutely, yeah, we should do that. Okay, I'm basically done. I have the tricks to make this faster later to do, but this is basically worry free boards. This fourth one is currently not used.
So, really naive question. In the paper, you said somewhere you use a proximity gap for powers. Where here is that?
It's in the paper, but in here we only need, for affine, we only need 2 for lines, because we only ever fold by 2.
Well, wait, but for k bigger than 1, let's say, right?
Yeah.
And do you need some kind of tensor?
Yes, they fold pairwise.
But mutual implies tensor is fine. Like I only need, like if I look at the theorem in like WHIR, like I only need the mutual that I showed you for the WHIR part. I only need the mutual that I show with 2, folding two words together. If instead, like the reason why we wanted the many case is that in WHIR we also have a compiler, which by the way can make these all black bots, and it's a cool trick. And in there, in the compiler, when I want to batch, I sometimes want to batch many functions. And there I want to have the proximity gaps for like many functions.
So you're claiming that if one, let's say we have k, what is it, 2 to the k rows, yes?
Yeah.
So you're claiming that using folding for affine lines alone, you can assert that if, let's say, one of those is not close, then the fold will not.
Exactly. So basically what's happening is that I'm applying like to each row, so at each fold I'm gonna be like folding this with this, and then this with the,
No, I get that it's a bunch of folds consecutively. The question is whether you need to argue anything.
So we need to do that, actually like mutual gives a lot of mileage, because mutual makes the sense that everything is very aligned here. So this is what allows us to actually do this. I mean, I'm not sure. I think that if you just have correlated agreement, is a bit more of a subtle.
But the work paper does have a theorem saying like if you have pairwise folding, then you can do this like repeated pairwise folding, and your error is going to be fine.
I mean, let me just put it this way: like, what if in the UDR you get mutual? Okay.
Yeah.
I mean, Angus and I had to sweat a bit to argue that you get tensor, you get a proximity gap for tensor combinations, even to bootstrap the result for lines to the result for tensors. So are you claiming like that you can get this for free, or?
I think so. Like in the paper we do it, and it's.
If I don't misunderstand, should be even in LDR quite straightforward.
Like with mutual, like I think you can do this quite well. Yeah, I do believe that. But maybe like we should double check at some
Maybe
point.
we talk after this.
Yeah, like, but I'm pretty sure that we can at least in the paper we have like we do like we do this tensor combination in many rounds, and it works out.
think
If there's
it's-
no bug in the paper.
Yeah, theorem 4.20 in the paper that you might be looking for.
Alright.
Yeah. 420, that's also nice.
Yeah. 10 minutes early.
Yeah, it's very coincident. Okay, so how do we finish all of this? Well, we have committed to something here. We've run something which gives us a bunch of linear claims. I wonder if we have a protocol which combines a lot of linear claims and does things with it. Turns out you do, so you just run WHIR again. And you do it a bunch of times until you get to the end. At the end, you will have like, at the end you just send whatever you have, so the final value, and then you check the some check claims about it. So there's one less trick that you need to think about or no. That is like, suppose that I have this claim over here. So, okay. These claims here, when I finish the sum check, they're really easy to evaluate because this is just, this becomes a quality of SI at gamma, where gamma is the entire randomness. So I just evaluate it. An equality polynomial is easy to evaluate. Let's look at that claim. So this claim is like sum of G RS of X beta times P at beta. So when I finish my sum check, this will end up being like something like the multilinear extension of GRS at gamma times P at gamma. This thing I'll actually get from WHIR for free. So I need as a verifier to compute this. This is where like the tricks come in. So it turns out that for read Solomon code, GRS at X gamma is exactly equal to the quality polynomial of the Pao vector of X at gamma, where this is the vector X squared, X to the 4, up to X to the 2, or say K minus 1, something like this. So this is like the binary decomposition vector. It is equal either the EQ polynomial or the select polynomial, depending on, because this depends on which Reed Solomon encoding you do. So in the current WHIR implementation, we are doing this encoding where I take my evaluations, I convert them into coefficient, and then I encode them. In this case, EQ is the right value. If instead I use the other version, I have like I have this other cute polynomial which is called the select polynomial, which is just product over I of what is it? Xi times yi plus 1 minus yi. This is for comparison, the equality polynomial is xi plus times yi plus 1 minus yi times 1 minus xi. So, yep, turns out this works. And the reason it does is because it's select polynomial. Basically, you can think that it multiplies together like if you do select at Pao, it kind of like exponentiates this depending on the on B, and it's a not too bad exercise to try. Yeah, and with this together, like this is all WHIR. Then the rest is just parameters and figuring out tricks to make this faster. And maybe I can mention a couple of tricks. I don't know how much time we have. I've kind of lost track.
I think 15 minutes.
15 minutes.
Okay, so one trick is that I'm gonna need to do sum checks of these kind of claims. So a few of these claims, they're like this equality times something. This we have a lot of tricks about. There's like the Justin's papers, this kind of like tensor structure, like kind of quite nice. This thing here is a bit more gnarly because these are like, you know, there are many of these. So first of all, there are like, there's many of these claims in the first round. So there's usually 100 in the first round, I want to say 14 or 15 in the second round, then 10 and so on. So there will be a bunch of these claims. They're like on a smaller hypercube, so this makes things already easier. But also, this is not trivial. The kind of nice of observation that you can do is that GRS time Q, you already have. This is the encoding P that you can get from the folding. So what you can do is you can reuse this to compute all of these at once. So you can basically do one work to compute this value, and then the values outside don't really bother you in any way. It's kind of like the same trick that you do in hyperplonk when you want to batch like challenges over the binary hypercube. So this is one trick that you can do to speed up this part here.
For the prover.
For the prover, yeah. Yeah, for the verifier,
The verifier has to do this thing on the right.
yeah, the verifier, the only thing you can do is like JKR all this stuff together if you like JKR.
Correct.
Yeah. So that's one optimization. Another optimization is that if you look at all these things, like the only thing that the verifier needs to do at the very end is evaluate these equality polynomials. So in fact, this protocol, like WHIR, basefold, and similars, like Ligarita as well, they give you really an inner product commitment scheme.
Correct.
So what I can usually do is that in a lot of protocols I have like, you know, I send a witness, say Spartan for example. Spartan does one first prod check, sum check. It's kind of like a sum check of the to check A x times B z minus T z is equal to 0. And then it does a lean check protocol, and then it does a PCS protocol. So it turns out that since these things are like, this is a inner product commitment, what you can also do is like, just do this. So the PCS, you can, like roughly this lean check is kind of like a check to check that the like, some claim of this form. And yeah, I mean, the lean check usually reduces this to a claim on A gamma beta and a claim on F beta. This is what these things usually do. And usually you prove this with a PCS. Instead, you can just forget about this and just run the WHIR on this claim directly at the start. And this allows you to save like one round of like the round of sum check that you would do here. So if this was from 3 log n round, you get to 2 log n rounds. So this is one optimization you can do, and this is good to save latency, for example. Yeah.
Can I? Oh, I was going to open up the Ligarito bag of tricks.
Yeah.
So now that you have WHIR in 3 boards, you can get the Ligarito in just as many. The first thing they do is comes from a different line of work, so there's no out-of-domain samples, and they just do more repetitions to get, you know, like smaller distance bounds. The next thing you can observe is actually we've been using RS codes, but they're not special other than for their distance property. Like the only thing we needed was interleaved codes. So Ligarito says use any code you want.
Well, you need a proximity gap too.
Yeah, exactly. You need a proximity gap, but otherwise that's it.
Yeah.
Which all codes.
Up to
1.5.
Yeah.
Parameter
Yeah.
like deal delta 3, 4.
Yeah. The only difference you have is like this statement here, this GRS, which you might not be able to express in a nice way. And this is where, like you said, you can use GKR, and these are protocols like Blaze. Essentially, that's what it does.
Yeah.
The other thing to observe with the implementation is actually they don't really think about polynomials. They just care about the evaluations of the initial thing over the hypercube, and that's kind of all you need. You need polynomials in the sense that you're going to be encoding, and that's the only time you have to think about FFTs. But otherwise, you never really need to think. These multilinear polynomials don't need to be materialized ever. And I don't know if that's something you do in the code.
We are working with choosing our polynomial.
Yeah, so I think you can just work with, sorry?
Data.
Yeah, data. You treat your polynomial first as a vector, and then you'll reshape it into a matrix to then be encoded. Likewise, when you're doing these partial evaluations in your sum check, it is just about reshaping the initial thing into a matrix, and I think it's just a matrix vector product afterwards. With, I think from Ben's papers, you'll find like this tensoring structure to have EQ as a vector. And I think you might be able to save some time there.
Save sometimes in the construction of the EQ polynomial, right?
Yeah, or just in the evaluation of this P of gamma and the rest is free.
Yeah.
You don't need to think of polynomials here. This is still like matrix vector operations. So if you have a fast matrix vector like backend, that's all you need to do.
Instead of having
Instead of materializing some multilinear and partially evaluating the multilinear, and then having that as your cube.
Yeah, I think there's a lot of tricks that you can do for like good, like if you do good matrix vector things.
That's all you need. And the only time you get out of that is when you want to encode.
Yeah.
If you have something better than naive matrix vector multiplication.
Exactly. Like if you think about it, this is like this protocol is actually a very surprising thing that these are in a sense they're code agnostic protocols in the sense like that you don't really use much of the structure of the code apart from it being linear. The rest is kind of like you get it for like efficiency for the good FFTs and all of that, but in reality what you really need is any code would work here with different verifier like efficiencies.
Exactly. This is just
and very, very surprising that you would think that like if you use a protocol which leverages very much the structure of the code, you would expect to get something better than a protocol which kind of like could pick any code inside there. And
like you do leverage the structure of interleaving and this like pairwise folding.
No, but
like that's where the structure exists.
Interleaving is a generic technique you can put on any code.
Yeah, it's the pairwise folding.
Yeah. No, but it's still like
the meat.
But it's still like
So you would need more structure if you wouldn't call it matrix-wise, but a single row.
Yeah.
Because then you need structure to decompose.
No, single row you cannot
into
do.
smaller things.
But actually, so when you take a polynomial, univariate RS, and then you sort of fold it, you are kind of you're taking this matrix, you're putting it in one row, and then you're breaking it back down, right?
Yeah. For me, this is a new learning actually.
Yeah, it's kind of interesting to me. You can like take any code and bootstrap foldability on it, and then
you don't even have to talk about foldability.
Yeah, because just interleave.
You just commit interleave. You
Yeah.
commit in
Everything is
smaller
interleaved.
chunks per se.
Yeah. Interleaving is all you need.
Yeah.
And it's very surprising and doesn't make sense to me, but
code switching idea is also that, right? Like Ron's paper, like Blaze is based on these things.
Angus, I don't know if you agree, but if we treat that like no more as a polynomial but vector matrix product, maybe we can even apply packing throughout this kind of strategy even faster.
What is packing?
Yeah, that should work. I'm sort of also I think there's some interesting things we can do with the first round as well.
Because right now we just applied CMD for the very low primitive like hash function and multiplication of extension field, but maybe for stuff like matrix vector multiplication.
That's all you need. All you need is a very fast matrix vector product.
The issue in that matrix vector product is also memory bound.
Yeah. Not my problem. I just told you what I know. And the rest is for you.
Yeah, I think in general, like these are protocols that could also be, minimizing the number of memory passes that you do in these things, and that, like, for example, one of the things that we saw at StepSync is that in the GPU setting, so I'm not sure how much it transfers to the CPU, is that the sum check polynomial computation, doing it at the same time as which you're doing the folding of the challenges, is something that turned out to improve latency quite a bit. So this is like when I'm computing So I compute H1, then when I get gamma 1 and I need to compute H2, like I both fold and compute the H at the same time. And this turns out, like reducing like memory, like passes, turns out to be quite nice.
So in one of the slides before, there was parallelization strategies. That's one of the issues with RAM today. It doesn't support spawning and syncing. It only supports parallel loops, I think. And there was some kind of RAM plus future that has been pending for like 6 years now.
Woo! Rust.
Quick question, maybe oriented towards WHIR 2.0. Have you guys been looking at Fix or Fax? I forget which one is the IOPP. They have like just a different batching technique. Is this something that's applicable here and will make any savings?
Yeah. Can you let us know about
Yes.
a bit more what you think about WHIR 2.0? Like,
Sure.
yeah.
So,
Jaguar.
so I think like so Fix and Fax is a wonderful paper. They did not really focus on concrete efficiency, so there are some deals, but you can think of it in many ways. One of the initial way you can think about it is that it does like a blaze-like step of course switching, and then kind of like changes to the yeah, it changes to WHIR exactly. And this is kind of nice because the only thing in the large alphabet regime, the only thing which is not optimal for WHIR is like the prover time. So using a different code with a better encoding at the start ends up helping. So the batching technique that they have is about like when you have multiple evaluation, you bring them together, right? So I think this is something that you can do like when you do all, so here when, well, actually here, yeah. The batching that I did here is kind of like the most naive possible version of batching. Because if you think about it, the complexity of the claim, you know, the verifier still has to work a lot at the end because it needs to kind of like do like, you know, if I had T1 and T2 claims, I have to work T1 plus T2. Yeah.
I think we shouldn't batch in the first round.
Sorry?
I think we shouldn't batch in the first round.
That is also possible, yes.
I think we can make this a lot faster. If we
Yeah,
do
because
that.
you don't do an extension field multiplication.
Don't do any extension field, and then also let you play around with AQ. Like if you start in the first round proving B subjects and only batch after the first round.
I agree. I think that's nice.
Yeah, so everything in the first one will be by basically.
Well, two things.
Not only that, also we can get rid of all FFTs. We can get rid of the painful stuff in the first round because you can pull out the EQ, like you can factorize the subject.
Yeah, because you don't have the epsilon anymore.
Because there's no sum.
Yeah, but you can also do it like virtually, right? I just compute everything on the base. I compute the subject polynomials for each one I'm in the base, and then I set the
polynomials is painful, right?
But you know, they're tiny. They're free.
No, they're large polynomials.
No, like I mean H1 and H2 and H3.
I think if you're skip, where they're now potentially.
Sure. I was thinking of like the multilinear case. Yeah. What was I gonna say? Yeah. So, for example, when we were doing accumulation later on, this type of folding does not work because if you're accumulating things, then the number of claims is growing, and at one point the verifier is like doesn't have too much thing to do. So there we had to use a different folding. This is the hyperplong style of batching, which is similar to the one that Fix and Fact do. And it helps. The kind of annoying part is that as far as I can tell, for that batching you require like a log n round because you need to run a sound check. So, you know. So in this particular case, because these EQ polynomials are also cheap to evaluate, it doesn't really matter. If these were expensive, they were RRA, for example, claims, what you would want to do is actually batch them in a similar way so that you only have one claim at the end to care about. Well, one claim per RRA code that you use. So this is one of the issues. Okay, so
not super helpful.
So as far as I can tell, not super helpful. Emil, because you've been there and that probably.
Yeah. Sorry.
There is something here. When computing the subject polynomial here, it's a degree 2 it's a degree 2 polynomial. So we need 3 points. And currently the implementation, we use the fact that we know if we call it f, we know f of 0 plus f of 1 equals and we know this value. But I believe with some work we can actually know f of 0 and f of 1.
Yeah, because they already computed beforehand.
Exactly.
Yeah.
And so, for instance, when about the out-of-domain samplings, when you compute the value, you need to evaluate your polynomial on this out-of-domain point, but you have like the obvious algorithm is a recursive approach on which you will evaluate half of your polynomial on the point and half here, and you combine the two. But instead of combining and forgetting the evaluations, you keep track of the intermediate evaluations, and using these facts, you can know f of 0, f of 1, and so you only need one evaluation of this sum check polynomial, and so you divide the work by 2, because in the current implementation you need 2 to the power of n sums, and you can do 2 to the power of n minus 1.
Yeah. Yeah, this is something that we should try, and I think it's a very worthwhile thing to do. Yeah. Similarly, here the encoding gives you already something, so you probably can also use it here. Yeah. Like if you draw the matrix vector things, you can see these things quite nicely. Very, very nice. So, okay, regarding WHIR 2.0, maybe I can give you like some intuition, some things which are true, some things which are not true, and some open problems. You know, you'll have to figure out which one is which. No, I'm kidding. Okay, so I said before, like one of the talks, like IOPs and codes have a lot in common, and in particular, now we have IOPs and codes end up having like, you know, I can make, if you give me any code, I can give you an IOP which is almost as efficient as the code. So it's true in asymptotically and in practice. So. There are many, so first things, folding. So I want to distinguish two different regimes in which we can do IOPs, because they're the only two, you know, is how many times you encode the witness. So I give you a code, and you have a witness, and I have to figure out how many, I will have to encode it at some point because error correcting codes are necessary. And I want to figure out, you know, how many times I encode it. And there's two ways of doing things. So this WHIR is in like this single encoding pass. So if my witness size is n, my like I will commit to something of n divided by the rate of the code. In this setting, there's only one thing that I know to do, which is to fold. So it is to do something which either in the Solomon case or like in the interleave case, I want to shape my stuff in a matrix like this, and I end up having this fundamental trade-off that I would like to, like, if I want to fold a lot, I need to set my k to be large, but then my verifier pays a lot. So I can set this to be square root of n, but then my verifier pays square root of n, and then I get Ligero. If I choose the k to be like constant, I get one version of WHIR, one version of Ligerito. The optimal setting in WHIR that we could find is setting this to be around log of n. And this gives you like, you know, the verifier with log of n things. Who cares? It's like 30 field elements, that's fine. If I do more than that, then it turns out that I can play a bit, get something slightly, maybe better asymptotically, maybe even just very slightly, but it doesn't really do much. So in this setting, like, in this setting, this is all that I know to do, and in that sense, like, if you look at the asymptotic things, like WHIR has got like quasi-linear encoding time. This can be improved, but I'll come back to that for a moment. The query complexity is O of lambda, so in fact, it's like, I want to say, it's probably just lambda plus little of lambda, something like that. I don't know exactly what we have, but it's basically lambda. It's not the constant is either 1 or 2.
Don't look in this direction.
Sorry? No, we're pointing at Elon. But Elon, we don't do constant, so it's yeah. So the number of queries that you end up getting there is almost optimal. And if you look at the verifier time is roughly like the number of queries times how much you read in each query. And you know, we know that each verifier, you know, if you read something and doesn't use it, it's a stupid verifier. So this is kind of like a lower bound on what we can do. So in that sense, in this setting where I said where I only encode once, you can think of WHIR being extremely close to optimal. Even if I look at like if I send a code word at a certain return rate, or like the first round of fry without anything else later, if you look at proof size, this is like kind of like WHIR is like 1.4 times worse than this thing, which is obviously too good to be true. So, yeah. The encoding time, like you can choose different codes. Different codes have better encoding time than with Solomon codes. And the kind of issue is that you usually end up getting a worse distance rate trade-off than with Solomon code, because RS codes are MDS, so they have like the optimal trade-off between rate and distance.
What do you think, for example, as example of other codes that you have in mind?
So RRA codes, array codes are great. I really like them.
They don't have a mutual agreement.
Sorry?
You lose when you use RRA, even if they have the distance, because they don't have a good.
Exactly. That's the other problem, that we don't know good mutual creator agreements for these other codes.
To 1.5 Johns.
We know to 1.5, but not to Johnson.
Yeah.
So like my number of queries ends up being like, I think like for example in Blaze they need to do 1,000 queries in the first round, while you do 100 with Solomon, which is yeah.
Just a quick question, circling back to that WHIR seems to work for arbitrary codes, right? If you just reshape the matrix and commit that way. How do you interpret, the previous oracle? Now, and the domain, the projected domain in some sense, which is not a subset of the new commit domain.
Yeah,
so how do you interpret something that is out of domain in the univariate sense, as in with Solomon, as how to ask what you have committed for that out of domain?
So so you just do this, right? So say that P is my message, and I want to say like when I encode P with an RRA code, I get the same value as the fold. I just use here the generating matrix of the RRA code.
I can't follow your notation, but
yeah, evaluating out of like a multilinear out of domain is a linear operation.
Yeah,
encoding is a linear
I fully
operation.
agree.
Yeah, encoding is a linear operation as well.
But here the point on domain, we have something. This is the commit domain of the code. There is is there connection with the hypercube or there
no, I don't think it matters. It's just that these operations are both linear and you can do them in any order you want.
Yeah.
You can first encode and then evaluate, or first evaluate then encode.
So wait a second. So we have the commit domain of RRA code, for example, and we have arranged already our long code word. Actually, we have shaped as a matrix, but still it lives over that domain.
Yeah.
So how do I check consistency between the next oracle?
So this is exactly what I have here. So if you have like, so I have a code. So when I fold, my folded code word is the encoding of the folded message, right? Because it's a linear operation.
Yeah.
And then what I want to check is that to check that the new message I'm sending is really the folded message. I'm going to check that the encoding of the new message is equal to the encoding of the folded message. This part I can get from the queries from before, because I just get it from here. And this part, I'm just gonna rewrite it as this linear equation, because I have I have G at P. This is kind of like, and I care about the X entry of it, and this is exactly the equation that comes out here. And this maybe should have been Q and not P. Yeah, Q, not P. So if I reinterpret the thing that I care about as a linear constraint, I just get exactly this equation, which is a sum check thing, so I can just continue going on with it.
I can't really follow, but I will meditate.
I can. Yeah, we can do it later on.
I don't want to block now.
So technically speaking, we're above time. So we have 20-minute break time for anyone who wants to grab a biscuit or a drink. But if you want to continue the discussion, by all means, feel free to continue as well.
Thank you, Justin.
Thanks.
Yeah, so just to finish this part on WHIR 2.0. Yeah, so the code with linear encoding time, they typically end up having a worse distance rate trade-off and worse mutual correlated agreements. So what this ends up being is that the verifier and the proof size end up being much larger. And the worse distance rate trade-off also means that like you have to do more hashing. And depending on your implementation, the FFT is a bottleneck or the hashing is a bottleneck. For example, at SP1, SFTs were not a bottleneck. It was not really the thing that was hurting us.
I think this is.
I think I now understand. So
I think
of every
for us also the case because we use Poseidon for hash for recursion processing.
So the hashing will be much more expensive. Yeah.
Is it fundamentally possible to have a linear code which is MDS? Is it possible or just we don't know it? But
No, so the
but it's not linear. Like
no, it's not linear. It's quadrilinear FFT.
What?
Quadrilinear
Oh,
probability.
sorry. You mean a code? Sorry.
linear code obviously, but with linear encoding.
Sorry.
Which would be MDS? Is it fundamentally possible or?
It is fundamentally possible. We have some codes which have linear encoding time and they're either MDS or near MDS. But this code, they come from like a line of work on distance amplification. And if you like, they're very practical.
Okay, and is there a chance that someone finds like a good code which is linear time and MDS?
Sure.
Okay.
You can also win the lottery tomorrow. It's,
Okay.
no,
Or you can solve the proximity gap.
no, it's like it is possible. Like we don't know too much, but you know, it is my hope. I would love to live in a world where you have like an MDS, completely efficient, linear time encodable code. But as far as I can tell, this is like a big open problem in coding theory, which is has only seen it's a closed problem, but it doesn't have a concrete answer.
Okay.
Yeah, as far as I can know, no. And yeah, which is very annoying, by the way. This is extremely annoying. Yeah. The other option is like I can start thinking of encoding more than once. So I can, instead of having an interleave code, I have a tensor code. There's some beautiful lines of work in both like circuit proofs, in both like theoretical computer science of using tensor code to get this structure. The issue is that, as far as I can tell, there like you get some issues in that. First of all, if you think about the tensor code, the distance deteriorates with like so the distance is the product of the distance of the code that you have, and the rate also like squares. So what you end up having, you also end up having like you can fold more. In asymptotically, this folding allows you to do better. You can get IOPs which are optimal in the small alphabet regime. But concretely, like the constant that you get on query complexity tends to be such that effectively, like the verifier time, unless for like extremely large or the argument size, the asymptotic don't really kick in until you have like an extremely large distance. And until then, like WHIR is better. So once we are like in a world where we're proving instances of cycle to the 40 to the 50, I don't know where the trade-off is. Like it seems that, like to me, at least my intuition is that the single encoding way is the way to go. Now, the exciting question is whether like we can fold by more than logarithmic in each step by only encoding once. And I have no idea whether we can do that. I have no clue whatsoever, nor any ideas. So, but I cannot rule it out. I've tried proving some impossibilities, but I haven't managed to. So it is still wide open.
What do you mean by encoding once?
Like my proof size, the proof size of the system is kind of like the witness size divided by the rate. So you give me, I give you any code. And you can only afford to write a proof size which is kind of like size O of n divided by rate. And I don't want to have like O of n divided by rate squared, for example. I really care about only performing one encoding. Yeah. Okay, class is missed.
Thank you, gentlemen. What a masterclass. Thank you so much.